In this video, we're going to continue talking about finite and infinite sets and cardinality. So recall that we defined a set to be countably infinite if there's a bijection between that set and the natural numbers. So if there's some function f mapping a to the natural numbers that's a bijection, a one-to-one correspondence, or f mapping the natural numbers to a, either way. In the last video, we also proved that if AI is a finite set for each I, then the union of those finite sets is finite, and the Cartesian product of those finite sets is finite. We proved that if each AI is countably infinite, or is just countable, so countable can be countably infinite in one-to-one correspondence with the natural numbers, or finite. So if each AI is countable, then the union from I equals 1 to infinity of the AIs is also countable. And we proved that if each AI is countable, then the finite Cartesian product of the AIs is countable. Further, we said that if f is a function that maps a to b, then if f is injective, if f is one-to-one, then the cardinality of a is going to be less than or equal to the cardinality of b. And again, that's because for each element of A, there is an element of B. We might not be hitting all of B. It might not be surjective. So just being one-to-one ensures that the cardinality of A is less than or equal to the cardinality of B. If F is surjective, then that means that all of B is hit by the function F. And that means for every B in B, there is some A in A. And so that tells us that there are at least as many elements in B as there are in A. So, there are at least as many elements in A as there are in B, because for each one of these, there is one of those. So the cardinality of A is greater than or equal to the cardinality of B. So I'd like you to kind of keep these things in mind and think about whether you can, maybe not necessarily do the full proof, but does any of this give you some intuition to show that the set of rational numbers Q is countable? So I'd like you to pause and maybe just think about this for a little bit. Think about whether any of the ideas above might help us prove this, and then we are going to do the proof in a moment. Okay, so let's prove that Q, the set of rational numbers, is countable. So remember that Q is the set m over n, such that m and n are in the integers, and n is not equal to 0. We want to show that this is countably infinite. One way we could do this is by making a function going between the integers cross the integers minus 0 to the rational numbers, to Q, and we could define that function as such. We could say f of the ordered pair of integers m, n is equal to m over n. So we could think about that. Now this is going to be surjective. This is surjective. Notice it's not one-to-one because, for example, f of 1 comma 2 is the same thing as f of 2 comma 4. So this is not going to be a one-to-one function, and that's okay. But it is surjective. It is going to hit every rational number. If m over n is a rational number, then m comma n is an ordered pair in z cross z minus 0. So this is surjective, and so by what we said above, that means that the cardinality of z cross z minus 0 is going to be greater than or equal to the cardinality of the rational numbers. And what else do we know? We know that z is countable. So we proved in the last video that the set of integers is countable, that there's a bijection between the set of natural numbers and the set of integers. Actually, I believe showing that that's a bijection is a homework problem. And so if that's countable, a subset of that is also countable. And so we've got this set is countable, has cardinality greater than or equal to the set of rational numbers, and therefore Q is countable. we know it's infinite, in fact, so it's countably infinite because there are infinitely many rational numbers. As we said, we know that if each AI is countable, then the Cartesian product over a finite number of Cartesian products AI, so A1 cross A2 cross A3 ... cross AN, will also be countable. And we use that above to show that the set of rational numbers is countable. However, a countably infinite Cartesian product of finite sets is not necessarily countable. So that's saying, okay, if we, instead of going from I equals 1 to n, we go from I equals 1 to infinity, and then we take the AIs, then if these AIs are either finite or countable, then this is not necessarily countable. And in fact, we're going to show this with kind of the smallest AIs you can think of, other than either empty sets or singleton sets. We're going to show this with the Cartesian product of the set 0, 1 crossed with itself from I equals 1 to infinity. So just to think about what that set looks like, if x is an element of this Cartesian product from I equals 1 to infinity, that means that these kind of elements would be of the form, 1, 0, 1, 1, blah, 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 an infinite sequence of zeros and ones. So we're going to show that the set of all things like that is not countable. In other words, it's uncountably infinite. To prove this, we're going to prove this by contradiction. So suppose, for contradiction, that this set is countable. So in other words, if it is countable, it would have to be countably infinite because it's clearly at least infinite. So suppose for contradiction that it's countably infinite, and therefore there is a function or a bijection f mapping the natural numbers to this set from I equals 1 up to infinity of this Cartesian product of 0, 1. So suppose for contradiction that this is a bijection. Now we're going to prove that there is no such function f. We're going to prove that no such bijection can exist, which is a tall order. So here is how we're going to do it. We are going to define a particular set x. We're going to define a set x. We're going to define a particular element x, and x is going to be an element of this set, this infinite tuple with elements 0 and 1. So x1, x2, x3, ... forever. That's an element of this set that we're trying to prove is uncountable from I equals 1 to infinity, the Cartesian product of sets 0, 1. And we're going to define it in this way, so such that xi is going to either be equal to, of course, 1 or 0, but it's 1 in the case that the ith coordinate of f of I is equal to 0, and it's 0 in the case that the ith coordinate of fi is equal to 1. And this is, again, based on the idea that we have supposed for contradiction that there is some bijection, so that's the f that we're talking about. So suppose there is this bijection. Now let's think about this particular element xi, or x, and note that, yes, x is an element of this set. What we're going to show is that then x is not an image of any element of the natural numbers, and therefore this function cannot be surjective, therefore no such bijection can exist. So that's what we're going to show. To just think about why that's true, just for example, so this is not really part of the proof, this is just kind of an example to just understand what this is meaning. So example, let's suppose that f was mapping the natural numbers to the set I equals 1 to infinity of 0, 1 in the following way. Let's suppose that f of 1 was equal to, let's just say, 0, 1, 0, 1, 0, 1, dot, 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 forever, of course. F of 2, let's say, is equal to 1, 1, 0, 0, 0, blah, blah, blah. F of 3 is equal to 0, 0, 0, 1, 1, 1, blah, blah, blah. And F of 4 is equal to 0, 1, 0, 0, 0, blah, blah, blah. Okay, so that's enough to tell us, at least the start of what x would look like. So f is continuing, f is defined for all natural numbers, but we're just doing this to help us think about what this element xi looks like. So what does xi look like? Then xi would be, okay, so in its the ith coordinate is defined by f of I. So the first coordinate is defined by f of 1, and because f of 1 is equal to 0, or the ith coordinate of f of 1 is 0, that means that over here we have the opposite coordinate. Now f of 2 is equal to 1, and therefore x2 must be 0, the opposite coordinate. F of 3 is equal to 0, and therefore x3 is going to be the opposite. And f of 4 is 0, so therefore this is a 1, and so on. So this is how this element x is defined. And clearly this is an element of this Cartesian product I equals 1 to infinity of 0, 1. And note, how is this element defined? It is defined such that it's going to disagree. We saw that it disagrees with f of 1 in the first coordinate. It disagrees with f of 2 in the second coordinate. It disagrees with f of 3 in the third coordinate. And so we see that x disagrees with f of I in the ith coordinate for all I in the natural numbers. So x disagrees with f of I for all I in the natural numbers. And that property is not just true for the particular function f mapping the natural numbers that we defined above, but however f was defined, because of how this x is defined, this element x is defined so that x disagrees with f of I in the ith coordinate for all I in the natural numbers. And therefore, it's the case that x is not equal to f of I for any I in the natural numbers. And therefore, that means that no f can be surjective. So no function f mapping the natural numbers to this Cartesian product I equals 1 to infinity of this set 0, 1 can be surjective because we've got this element x in this set such that, so element in this set such that x is not equal to f of I for any I. So no matter what function we define from the natural numbers to this Cartesian product, it cannot be surjective, therefore no bijection exists. So therefore, no bijection from the natural numbers to this Cartesian product I equals 1 to infinity of the set 0, 1 exists, and therefore the cardinality of the natural numbers is not equal to the cardinality of this set. So it's not equal to the cardinality of this set. This set is clearly infinite. So this set I equals 1 to infinity of 0, 1 is infinite, but it is a different cardinality of infinity. So it's a different cardinality of infinity than the natural numbers, than the integers, than the rationals. The those are all the same cardinality. This is a different cardinality, but this is uncountably infinite. So this is an uncountably infinite set. A corollary to what we see above is that the set of real numbers R is uncountable, so is also uncountably infinite. To see that this is true, we're going to define a function, f mapping this set we've just been talking about, the Cartesian product from 1 to infinity of this set with two elements, 0, 1, to the real numbers by the following. So f of a1, a2, to infinity is equal to point a1, a2, a3, forever. So each of these things is a real number, right? So for example, f of the tuple 0, 1, 0, 0, etc. Would then be equal to the decimal value 0, 1, 0, 0, whatever this is forever. So since this is a real number, that tells us that f of this product, this Cartesian product, I equals 1 to infinity of 1, 0, is a subset of the real numbers. In fact, a really small subset of the real numbers. It's only decimals that only have zeros and ones in their expansions. All values between 0 and 1 on the real number line. So it's a very small portion, like a subset of the real numbers. But because this is countable and f is 1 to 1, for every one thing over here, there's only going to be one output over there. That means that the cardinality from I equals 1 to infinity of this set is going to be less than or equal to the cardinality of the real numbers. And so, therefore, the set of real numbers is uncountably infinite. Uncountably infinite, or we could also just call that uncountable. A further corollary is that the set of irrational numbers is uncountable. So, we know the real numbers is everything on the real number line. We know that the set of rational numbers is the set of fractions. So the set of irrational numbers, I, we could have a bold-faced I if we want, if that's the irrational numbers. That is uncountable. How do we know? Well, we know that the real numbers is the union of the rational numbers together with the irrational numbers, right? Every real number either can be represented as a fraction or it cannot. So if we suppose, for contradiction, that the set of irrational numbers is countable, then what do we have? We have a finite union of countable sets. So finite union of countable sets is countable. We know that by one of the theorems we spoke of at the top of this episode that we proved in the last video. So the finite union of countable sets is countable, and so this would imply that R is countable, but we just proved that it is not. So that means that we know Q is countable, we proved that, and so therefore the other part of that union, the set of irrational numbers, is uncountable. So is uncountably infinite.